function, given that you build a good network. So there's no restriction as a sort. You can approximate any function of your choice. So generally, how does a neural network look? You have basically an input layer, uh, and then you would have an output layer, which is what we will extract as a prediction. And between those, you'll have a series of hidden layers which do some computations with the input data. They do some nonlinear transformations as well. Through and how are they transformed is determined by weights which are actually learned through the process of training, right? You can also have more complex networks like RNN, CNNs, transformers, etc. But these are the building blocks for those as well. And the training process here, how does it look? So let's say you pass in some input to the neural network. You have random weights initialized because the training is not done yet. It gives you some output in the final layer. So you compare what the output is with the input training label. You compute a loss, and then that loss is back propagated. It's distributed across every weight within the network, right? And this is passed to the optimizer. The optimizer determines how much to adjust each weight based on the loss we found. This happens iteratively until we minimize the loss to the extent possible, and that's when we have a final fully trained network. So yeah, briefly, that's what neural networks are. That's all I had on this. So we'll go to multitask neural networks. So multitask neural network, first of all, what is multitask learning? So there might be scenarios in which you have two very similar tasks to be performed. For example, in the example, one example we can think of is BERT, a language model, right? The way BERT is trained is it's trained on two tasks, which is next sentence prediction, and it's also masked language modeling. You predict the missing word between a couple of words as masked language modeling, which is a multi-class classification problem, and you also predict whether two sentences come one after the other. It's trained on these two tasks, and the idea behind that is that the model gets to learn the language better, right? Because it's trained on two separate tasks, they might have different learnings. So the idea is you train it on two separate tasks which are kind of related. Both need you to understand the language. So that's an example where multitask learning is used. Similarly, multitask neural networks here, we can take neural networks and we can train them on two tasks simultaneously. What we hope to achieve from that is probably there might be improved performance because two tasks can complement each other. They're related, and probably learnings from one task might influence the other. So it allows us to leverage the information between tasks. It also helps in generalization, yes, because you're learning different tasks, you can generalize better without overfitting to one task. And efficiency. So instead of maintaining two separate models, you can probably just have one model which gives you two outputs. These are the good parts of it, but of course, it's not beneficial all the time. Sometimes you might have tasks which actually don't help each other that well, or it might be difficult to train a model because the losses behave differently for the different tasks. So there are some we need to assess whether multitask learning is beneficial or not. It's not that it's always going to help you, but in cases where it helps us, these are what we expect it to give us, right? Um, So multitask neural networks, the kind of neural network we'll cover for this topic today is hard parameter sharing, which means that you have a group of shared layers for a task. For example, you have an input, and then you pass the input in through a common network, and then the whole network splits into three different heads. Task A, task B, and task C here, three different tasks. Each task will have its own loss function, right? So everything, and the idea here is that we'll have some common learning till this shared layers, and then from there on, we'll get into task specific learning within their own dense layers, right? And this is called hard parameter sharing. You might have other methods like soft parameter sharing where you don't have a group of shared layers, you have separate layers, but they have some connections between them which would help in transfer of knowledge. but we're not covering that for now. We're just looking at the simplest type, which is shared layers through hard parameter sharing. So here, how does the learning happen? The forward propagation happens as usual. You pass the data in through these layers, and then they're processed separately within each task. And each task will have its own loss. So you'll compute a loss for task A, a loss for task B, and loss for task C. All of these losses are added up, and that's what is back propagated throughout the whole network. So the loss you compute from all these tasks is added up, and then you back propagate that throughout the whole network, and the limits are adjusted throughout the shared layers as well as the task specific layers. Right. Are there any questions till now? Should I take a pause?
No, sir. I mean,
Okay.
you can like do the Q&A session at the end.
Okay, sure. Yeah, I'll do that then. Yeah, so that's what multitask neural networks are for hard parameter sharing. We'll implement this through code as well in this session later on. But before we get to that, we also want to explain this neural network. So we'll go over SHAP explanations. So before SHAP explanations, let's think about Shapley values, which is a concept from game theory. This is what SHAP explanations are built off of. So it's important to understand, I mean, at least have an intuition as to how this works. So now don't think about a machine learning model specifically. Let's just think about general concept, which applies anywhere. Then we can translate that to an ML problem. Right. So here, Shapley values is a concept from game theory, and what it tries to answer is, if I have a certain outcome, and I have a group of people or I have a group of members, how do I distribute that outcome to each member in the group? Like how much effort have they put in? What's the value they brought, and how do you distribute the outcome fairly between all the individuals? In more technical terms, if you have a coalition C that collaborates to produce a value V, how much did each individual member contribute to V? So by coalition, we just mean a group of members participating in the event, and then they work together, and we know that the final value they bring in is V. So how much of this V has come through each member of the coalition? Right. And just to look at an example of how we can come at the individual contributions for each member, we take the case of just three members in a group, right? And we know that if these three people work together, we have an output of let's say V123. That's the outcome. And let's say we also know if only 2 and 3 work together, the output would be V23, right? So what's the marginal contribution of member one? Like if we subtract these two outputs, it will tell us how much one has contributed to this specific coalition of 2 and 3. Right. So marginal contribution of member one when 2 and 3 are already in the group is V123 minus V23. And similarly, if I just take, I also know that if just 1 and 3 are in the group, they get an output of V13. And if only 3 is in the group, it's V3. So V13 minus V3 would be the marginal contribution of member 1 to C3. So if only 3 was there initially and I add 1, then V13 minus V3 would be the contribution of 1, member 1. These two would not be equal. You might think that the difference between these is just the performance of 1, and here the difference is performance of 1. That's not the case, because the value of 1 might be different depending on who's already there, right? Somebody who brings in a value of 100 individually, if there's already two people working on it and they all have a value of 80, I might bring in only 40 additional value. Everything I bring in, some of it might be covered by the existing members itself. So we can't say that V123 is equal to V13 minus V3 and so on. That's why we say it's marginal contribution over a given coalition. Similarly, for all possible coalitions, we'll have 4. Since you have 2 members excluding 1, you have 4 different possible coalitions. And and we have a marginal contribution of member 1 to all of these 4 different possible coalitions or combinations. how does Shapley value? What's the Shapley value of 1? The way they do it is they take an average, a weighted average, over all the marginal contributions of 1 to the different correlations, to all different possible correlations. So that's what it says here. We get the Shapley value of member 1 by averaging out marginal contributions from all the possible correlations of the given members. And this same process, we can get a Shapley value for member 2 as well by just considering all the correlations without 2 and taking a difference between the outcomes, right? This is the formula. I won't go over it, but this is telling us it's a weighted average of marginal contributions through all different possible correlations, right? So this is in the case of not in the machine learning context. In this, we know that if 2 and 3 are together, you have an outcome of 2, V2, 3. If 3 is there, the output is V3. This is all in the case that we know that. In machine learning, this might not be the case though. So we'll try to translate this and how it can be helpful for machine learning. So yeah, in ML, we have SHAP, which is Shapley additive explanations. This tells us that from the name, we can see that this is something which uses Shapley values. It's used to explain a model. We have an additive term here as well. So the additive term just tells us that the authors of this SHAP have modeled this case as a linear combination of different SHAP values of each individual contributor. So the overall outcome is just nothing but a linear combination of the individual SHAP contributions of the features. So let's just think about how do we translate this from Shapley to machine learning to SHAP. What SHAP tells us is, given that without any features, we would just have an average value. So if I have no information about the features in a problem, the best guess I can make is that the outcome is going to be the average value. So once I bring the feature in, how much would my prediction change? That tells us what the value of the given feature is. Right. So the SHAP value of a feature tells us how much has it influenced the model to predict a value different than the mean. That's what SHAP tells us. And the way SHAP is modeled is, so we'll just look at this equation. These terms are unfamiliar, but we'll go over what they mean. So G of Z prime is what is shown here. And G is nothing but the explanation model. It's the model which explains how SHAP is contributing for a sample. This is for one sample, by the way. For a sample, this is the relation. Z prime is the correlation vector. So correlation vector, you can think of it as vector of ones and zeros. In the example of, let's say you have 4 features for your model, it might be 1010, which tells you that only features 1 and 3 are present. I don't know about 2 and 4. So that's what Z prime is. It can be 1010, 1100, any possible correlation. And phi represents the Shapley value for each feature value. So since this is for a sample, what SHAP will give you is, for each sample, you'll have a feature and the feature will have corresponding value. So what does this feature value contribute to the final prediction? Since we should also keep in mind that SHAP is a sample level explanation. So SHAP works at a sample level. It's not a global explainer. It rather explains how each individual feature value for a sample is influencing the final prediction. Yeah, so that's how SHAP is represented. Now, if you think about it, Shapley in these five are Shapley values. So we know that Shapley values can be extracted in the manner shown in the previous slide. Like if I know what 2 and 3, if I take out one feature and look at the different possible correlations, I can get the Shapley value. But the problem here is just for 2 features, I had 4 different correlations. If I expand that to, let's say, 10 features, I'll have 2 power 10 for each feature value for each sample. And it increases exponentially. So it will become increasingly complex to compute these SHAP values. So that's what we're covering here. So G of Z prime is nothing but the model prediction, right? Explanation model, which is what the model prediction is, the trained model prediction. And when I say Z prime, it means that some features are there, some features are not there. But we know that for a trained model to make a prediction, you need to have all features. You can't just take out two features and tell it give me a prediction. It doesn't work. So how do we get the feature prediction for a sample which has some missing features in Z prime? That's something we look to answer. And also, as I mentioned earlier, for estimating SHAP value for each feature for a sample, we need to make two power m correlations. And then for each correlation, you need a prediction. So this becomes really expensive. So the authors of the SHAP library, and we'll go over one method which they have, which is called Kernel Shop. And this Kernel Shop, it tries to counter that problem by making a few assumptions to reduce the compute time for computing SHAP values. So first thing is, instead of going over all possible 2 power m correlations and then getting the contributions for each sample, instead you collect one sample from the data which you want to explain. You sample a few correlations. Let's say I have a data set with 4 features and one prediction. You will take a few correlations. You'll just say that 2 and 3 are missing, 3 and 4 are missing, 1 2 are missing, 1 is missing. You just make a few sample correlations, sample a few of them, not all 2 power m. And when you want to get a prediction for a sample, let's say of this sort, we know that the output for 1 2 3 through the model is V123. But how do you get the prediction for 2 and 3? You need to get some value for 1. And what it does is SHAP needs some background data set, which we decide. And that background data set, it samples multiple values from the background data set. And it uses that value here, gets a prediction, and does that for all the background samples and gets an average value. So I can take a value for 1 from the dataset, background dataset, get a prediction, sample another value, get another prediction, and so on. And you average out all the predictions. 2 and 3 are constant. So that will give you the average prediction of the model for 2 and 3 being fixed, which is a correlation, and 1 being averaged out for all the predictions. So that's what we do here. That's how G of Z prime is estimated. So for predictions and correlations which have missing features, sample possible values from a background dataset, which we give to the kernel shop. And you get all the predictions and average them. That's how you get it for a correlation with missing features. So once you have sample to correlations, you got the background data, you got the G of Z prime values as well. You kind of have a data set right now. Right, because you know for which missing features, how does G of Z prime look? This is the equation we have over here. And G of Z prime is you're calculating through the background dataset calculations. And phi is what we want to estimate. Zj prime just tells us which feature is present or not. So we kind of formed a training dataset now. You have a Y label, you have input features which are Zj vectors. And with this one thing is what SHAP does extra. It calculates a weight for each each possible correlation. The purpose of that weight is to give importance to a few correlations over the others in estimating the importance. And then after that, you fit a linear model, right? So you have your training data set, you want to estimate phi. So you can fit a linear model through minimizing this loss function. F of h of x is nothing but the actual model you have, which is the true label. G of z prime is the model prediction, is the estimated value from the background data set. And this pi of x is what the weight is for each correlation. This is, I don't have the formula for that here. I don't want to get into that detail, but it's like a regular linear regression loss function, sum of squared errors. But the only difference is that now you have a term weighing each possible correlation. And keep in mind, this is all done for only one sample to explain just a single sample in a dataset. Now, KernelShop has to do this for every sample which you want to explain. If I want to explain 2000 samples for my dataset, it needs to follow this process for each of the 2000 samples in the dataset. Yeah. Yeah. So that's briefly how kernel SHAP works. Uh, so once you minimize this loss function, you end up with the coefficient values, the coefficients which give you the least loss. So that's how the SHAP value is estimated for different features using kernel SHAP. If you think about this, there's nothing specific to our model here. We just need the model predictions. We have not made any assumptions regarding how the model is. So this is a model agnostic approach, kernel SHAP. Yeah, and which is why it's a little slow. We have other methods like deep explainer, tree SHAP explainer, which leverage the predictive model structure to get more optimal solutions or get more efficient solutions in quicker time. But this is the general concept which all of them follow. So I wanted to go over this briefly. Uh, yeah, this might be a little in depth, but having some understanding about this is good regarding kernel SHAP. Yeah. So this slide I just added, this is actually the algorithm as given in the documentation itself. Right, so I just added it here. It's kind of what I covered in the last slide, but in more mathematical form. Yeah. So I'll actually go to the tutorial itself, the code walkthrough. Just give me a minute. I need to share that screen. Okay, let me know if you can see my Jupyter notebook.
Yes, sir.
Okay. Yeah, so as I discussed, we'll cover two things in this code walkthrough. One is building a multitask neural network model, and then after that, we want to get it explanations using SHAP. So we're importing packages here. Let me know if the screen size visible. I'll just zoom in. Okay.
Excellent.
Yeah. So we're just importing packages where we need TensorFlow for building our model, scikit-learn for some data processing, and then matplotlib for plots. SHAP I'll import later. So in this thing, what we're trying to do is there's provided by UCI, we have online news popularity dataset. And in this, the basic task is given some information about a news article. We should predict the number of shares it has, the number of times it's been shared. Right? It's a simple regression problem. Just for the sake of making a multitask problem, I've taken if the number of shares are if greater than 10,000. I've given that it's a high shared article. So I'll just go over that. I'm doing some basic pre-processing here, removing outliers, looking at the distribution here. 95% of it is less than 10,000. So what I've done is, since it's a regression problem only, and I want to make a multitask problem out of it, I'm trying to do two tasks. One is a classification, one is a regression. The classification task should tell us if the news article will have more than 10,000 shares or not. So that's what we're doing here. The high share threshold is 10,000, and we know that 5% of the data has more than 10,000. So I'm creating a high shares yes or no column, which is based on the shares column. If it's more than 10,000, it's a positive class. If it's less than 10,000, it's going to be a negative class. So two tasks, which we have two target variables. So yeah, if you look at the data now, given the features, you have the shares, which is one problem, the regression problem. High shares yes or no is a binary classification problem. Okay. So once we have that, the thing is the data is all processed. We won't go over that, but it's already processed in the input itself. There's no missing values. So it's all well treated. We'll just pre-process it for the sake of the neural network because you have features on varying scales. We'll try to get them on a similar scale. So if you look at this, you have something in the range of 8,000, something in the range of 300, 100, which are very widely varying features. You have something on scale of 0 to 1. This will harm a neural network in its training process because each feature is multiplied by a weight, and that will make a few weights more prioritized than the others because of the input they're taking in. We want to avoid that, and which is why we're pre-processing the data. Uh, we're just making a train test split here. 10% goes to test data, remaining 90% to the training data. And the only pre-processing step I'm applying here is scaling features using a standard scaler. For those which have more than two, I'm not doing it. Less than two, I'm not doing it because they are binary features, 0 or 1, or they're between 0 and 1. They're actually binary flag features which have exactly two attributes, like data channel is bus, data channel is entertainment. All of these features are actually one hot encoded features, which is why they're like this. They can either be 0 or 1. I don't want to scale them, so anything which has more than two unique values, I'm going to scale them using a standard scaler. And that's what you're doing here. You're fitting the scaler on the training data and transforming the test data using it. Similarly for the outputs as well, for the regression problem where there's not the number of shares of the article, we're pre-processing that using an output scaler, fitting it on the training data and transforming the test data with it. So once we have the formatted data, you have two targets and you have standardized input features, we'll get into building the model. Just give me a second here. Okay. So I'll just go over what's the model structure which we're trying to build. So as we saw in the previous during the presentation, we're going over hard parameter sharing multitask neural networks. Over here, you have an input layer, you have some batch norm, you have a shared dense layer, you have two shared dense layers, and then you branch out into two different tasks. One is a classification task, and then you have one is a head for regression. So till this point, two dense layers are shared, and then after that, we have two more dense layers for each task. You have dropouts in between rail activations, etc. But this is an example of a hard parameter sharing network for doing two separate tasks. One is regression, one is classification. So that's the model we are going over here. So since this is not a traditional sequential model, we'll be using TensorFlow's Functional API. I'll try to go over this briefly, but going through the details as well briefly. So shared dense units list is those which have those layers which are shared. So we want one layer with 64 neurons, another one with 32 neurons, two layers in total, which are shared across both the tasks. And then you have a regression specific dense unit list, which is having 64 neurons and 16 neurons. And similarly for the classification task, you have 32 neurons and 16 neurons. These are shared and these are task specific, which come after the shared layers. This is a function I have for building the multitask model. You need the number of features for deciding the input shape, the shared dense units, regression dense units, and then there are some other parameters. The input layer, we're using functional API. So you're assigning each layer to a input to a variable, and that is going to be used in the next call of the next layer. So here, for example, you have input and number of features as the parameter here, as a shape. This input should be again passed on to the next layer, which will be using it, which is batch norm in this case. Right. I'm going to iterate over each of the shared layers, since after the input you have the shared layers. We'll iterate over them, and then for each dense, we want to tell it's connected to the previous layer. So shared X is what I have, and then the first dense layer and the shared layers connect to shared X. And then we have a ReLU which takes in the input from the previous layer, which is again shared X, this one. So what we're trying to do is we're trying to define connections in this network. We want to tell that this shared layer is connected to the batch norm, and this batch norm is connected to the input layer, and so on. Over here is where we need to tell that the regression dense layer is connected to the final dropout layer from the shared layers, and the first classification dense is also connected to the final dropout. So this is where the functional API will be useful. If I went through sequential, I couldn't do this part, but everything else can be done by its own. This part is what needs us to use the functional API. So once we have iterated over all the shared layers, you created a shared network over here. The final one is the shared X, which is dropout of 0.2. The regression head, the first layer must use the shared X again. So that's what we're doing here. Regression, if we have some regression task with some units, then we will define it as the first layer having is a dense layer, which takes in the shared X from the previous shared layers. And we do that process over here as well. Similarly, uh, yeah. So the next one takes, so first layer is taking in the shared X layer, and then we know the second layer should be connected to the regression layers itself. So that's why from the first layer, from the second layer, we connect it to the regression X in the dense layers. So this all of this part is to define just the regression head, which is this part. We want to ensure that they're connected only within their branch and not to any other branch within the network. The final output is a single value. It shouldn't have any activation because it's a regression problem. So the final layer, which we'll see, is just a dense layer without any activation. And yeah, that's the final output layer of the regression problem. Similarly, we follow the same process for classification. We ensure the first one is connected to the shared layers dropout, and then the subsequent layers are connected to the previous classification layer itself. The final output is going to be a single neuron again. This has to be transformed through a sigmoid because it should lie between 0 and 1. And that's what we have here as well. The final output layer is going to be a sigmoid layer. It's going to be transformed to a sigmoid function, and that value lies between 0 and 1. So with that, we've just defined how the model is connected, the architecture. And if you look at this as well, since it's a multitask problem, you'll have multiple outputs, one for regression, one for classification. We define our input as the first input layer we have. And then we have two outputs in this order. Regression comes first, then classification. So we need to be consistent with this order because we'll use it in the future as well while passing in training samples and getting metrics, etc. That's the function. So here I'm just passing in all those features to the model multitask model function, which will give me this model. And the model.summary is just a summary of what we saw in the diagram over here. This plot. Okay, so we have trained the model. We have defined the model. Now we need to train it. Before that, we need to actually define the optimizers. We need to define our loss functions for each classification for each task, and then the metrics for each task. So here, I'm just using an Adam optimizer with 10 power minus 4 learning rate. And in the compile, you pass in the optimizer. And here, this will be different for a single task versus multitask model. Since you have two tasks over here, each task has its own loss function. The classification task has a binary cross entropy loss, regression out. So these names I'm getting from the names I've defined within the network itself. Uh, so if you see, it's called PCLSF for the classification, regression out for the regression problem. So I'll use those names itself. And that's how the model knows that where to apply each loss function. PCLSF, we're going to apply binary cross entropy. Regression out mean squared error is what I'm going with. And we can also define our metrics to monitor our validation performance on for each task. Classification task, I'm looking at AUC, and for regression out, looking at RMSE and mean absolute percentage error, etc. I'm defining 500 epochs. That's because I have early stopping enabled. It's going to monitor validation loss. And if the validation loss does not improve in 10 epochs, we're going to stop training and we're going to restore the best weights. So that's the callback we have, and we're using that. And yeah, model.fit, taking in extrain dot values. For y, we need to pass in, as we know, y is actually two labels, the regression label and the classification label. There's a specific format which it needs, which I have here. It's a specific detail. It's not really important. You can see it in the code when you use it. But it's basically returning two arrays. Train wise is just two arrays, and test wise two arrays as well. The first array contains all the classification values, the regression values, sorry, and the second array contains all the classification values. That's what we pass for the training, for the wide part in both train as well as test. We have a validation data set on which we monitor our metrics and check for early stopping. So yeah, this training process, it took about, I think, less than 2 minutes or something on my PC. But the goal over here is not to build a good network. It's just to demonstrate how we can build it and how we can get explanations. So the metrics and all, they might not be great. Uh, yeah, because it's not an optimal network for the problem. We're just fitting a neural network for some multitask problem here. And more improvements can definitely be done. So yeah, we're just looking at the plots, looking at the regression output loss and the classification loss, which seem to have converged to a stable value. It's not going down anymore. We have prevented overfitting as well by early stopping based on validation performance. Looking at AUC, RMSE as well. So these are not important. These metrics might not be good. We're not really sure about that. So once we have that trained model, we save it in TensorFlow's default format. And just to show how the predictions look like, if I do a prediction on two samples from test data, I have an array with two elements. Uh, the first one has two predictions. Second one has two predictions. The first one corresponds to the regression output. Second one corresponds to classification. Both are on this scale because if you remember, we also scale the regression output using a standard scaler. So to get the actual value, we should inverse transform it using the scaler, which we won't do because our explanations will be based on what the model is trained itself. So our explanations are going to be built on this scale. Yeah. So yeah, once we have the trained model, we can get all the predictions from the model. And we're now interested in how do I explain the model for both of these tasks. I have a classification problem and I have a regression problem both within the same model, and I need to explain it using SHAP. So here I'm using SHAP's deep explainer. I'm not using kernel explainer. I'm using deep explainer because it's much faster for the neural networks. So I'm using it. It has similar concepts to kernel explainer, but it has a lot more. It's more efficient, and it utilizes the deep learning architecture to get better, to get more optimal explanations. I'm not totally sure about how deep explainer works, but we can think that the whole idea is still going to be based on that game theory explanation for Shapley values. So yeah, so now we know that we have two output values. What we should do is we need to segregate our model into the regression model and the classification model. So if you look at this diagram here again, all of this is going to be the common model. And then for the regression, we need to only take these layers on the left. The ones on the right are to be ignored uh, for the uh, for the regression model. And that's what we'll do here. We say the regression model is, this model is TF Kera's module. And this takes in model.input. We're defining model.input uh, as the, we know that model.input gives the first input layer. Model.output of 0 is the regression output. So that's what we defined. We know that the first outcome is going to be the regression output. So we say that the input is going to be model.input and the output is going to be modulo output of 0. So based on these two alone, TensorFlow can figure out what this is connected to, and it will infer all the connections and give us only this model on the left, plus the shared layers, which is what we want. So that's a regression model, which we have. We've taken a subset of the broader model. So if I try to predict using regression model now, I'll only get one output, which is the first entry. So now we need a sample data set. If you remember, we talked about background data in the slides. The background data is used to fill in the missing features by sampling from the background data randomly and getting predictions. So that's the purpose of this. So if when we take in coalitions and there are missing features, we get those feature values by sampling from this data set, the sample data. We take in 2000 data points. So any value for any feature, it's going to pick up from these 2000 data points itself. And then we have an explained data set. So as we know, SHAP is working on a sample level. So you need to tell it which samples it should explain. And based on that, it will tell you, it will give you the summary or the global feature importance or the sample level feature importance. So I've taken 5,000 samples for explained data. And to deep explainer method, we pass in what our model is, and we pass in the sample data, which is the background data set. This will initialize the explainer. This is something which we added to avoid errors. There's some issue with SHAP, so we've added these. You can ignore them. So you initialize deep explainer with giving it the model, and you gave it the sample data, the background data values. Now we'll extract SHAP values for the explained data set. That's what this part does. So this might take some time depending on the size of your data and depending on the algorithm you're using. If you're using deep explainer, it's faster. If you use kernel explainer, it will take a lot more time. So it's sensitive to that. Once you have that, you'll end up with SHAP values. So what SHAP values is since you have given 5,000 samples in your dataset, you'll have 5,000 rows, and you'll have a SHAP value against each feature value within that dataset. So 5,000 cross, I think we have around 60 features in this, 59. Have 5,000 cross 59 matrix, in which we have the contribution of each feature to each sample within the data. That's what this gives you. You have sample level explanations. So SHAP, once you have that, it's just about visualizing what the SHAP values look like. So we have a summary plot, which tells you over the entire explained data set, how does the algorithm perform, or I mean, how does the feature importance look like? So on the y-axis, we see mean of absolute SHAP value. So you take the absolute SHAP value and take a mean of it. And these are the features we see. But this doesn't really tell us, is it influencing my output positively or negatively? Right? We just know that the absolute value, it has some impact. We know that these are impactful features. But what SHAP has is it tells us the directionality as well. So does data channel is bus influence my outcome negatively or positively? That's something we don't know from this plot. So for that, we have this summary plot. So what this tells us, the way to read this is, let's say since this is for how many? 5,000 data points, I guess. Explain this is 5,000 data points. For 5,000 data points, it's going to plot them on this by a dot. Each dot is a sample. And a sample with a high keyword average value has a high mean, has a high SHAP value. So we know that for this tells us this sample happens to have a high value for keyword average, which is why it's red, and it's far to the right, so it means it's a high SHAP value. So this tells us that this feature, when it has a high value, it tends to positively influence your outcome. Similarly, the second feature, when the channel is entertainment, it's either a 1 or 0 feature. So the red means that it's a high value, which means it's 1. The feature value is 1, but when the feature value is 1, your SHAP value is negative, which means it's influencing your outcome negatively. So that's how you read these plots. The color of the point tells you if the features value is high, Where the point is on the scale from left to right tells you how much of a value it has or how much of an impact it has on the final outcome. So that is this summary plot. And the next thing is sample level explanations. So these plots are built using the sample level explanations itself. But this is what we want to visualize first because we want to know how the overall impact is. When we're interested in specific samples, we would come to sample level explanations. So here I had to copy paste pictures because these are being omitted once I upload it to a different place. So yeah, this is a picture I have copied and pasted for this index. I'm using index 20, which means the 20th sample in my data. I'm trying to see how do the features influence the outcome for this particular sample. So here, minus 0.08 is the final prediction from the model, which we have from our model. And this tells us how each feature is contributing. So n tokens title equals 1.23. It's the feature value. It's not the SHAP value. Similarly, average negative polarity minus 2 is 2.032 is the feature value. This seems to be affecting it negatively. It's pushing it to the left. This is pushing it to the right. How do you read this? What does this actually mean? For that, we have a function here, sample level details. So we know that n tokens title has the highest positive impact, and n tokens title is here. Its sample value is 1.23. If you look at the mean background dataset value, the background dataset which we provided initially to the SHAP, it's actually almost zero. So this sample has a higher value than the mean background dataset value by 1.23. The SHAP contribution is positive. This means that because I have a high n tokens title value, my prediction increased by 0.023 to the right. It's positively influenced. That's how you read this. Because we don't know if this 1.23 is high or low, but looking at the mean background value, we can estimate that, okay, this is actually higher than usual, which is why I'm having a positive contribution. Similarly, for this feature, average negative polarity, it's going to be last here. Average negative polarity, it has a value of 2.03, which is a high negative polarity score. The average value in the background dataset was 0.03, so it's much higher than usual, and that caused a negative effect on the shares, number of shares it had, the article. So that's how you read these plots. We looked at the sample level plot, and we also looked at the summary plots. This was for the regression model, and you can do the same thing for this classification model as well. Instead of defining your model as the input and the regression output, you define it as the classification output now. Model output 1 corresponds to the classification output. So this will give you the subset of the model which corresponds to the classification task. And we repeat the same process as nothing changes here, even though the output is classification problem output. SHAP doesn't really change. We follow the same process to get the summary level plots as well as sample level plots. Yeah. So yeah, that covers this. I I I've shared this with the team. I'm not sure what to do. I guess they will share it with you later on. But you can have a look at these codes to play around with proving the model or looking at SHAP, exploring SHAP's different kernels. A lot of things can be done because we're using deep explainer. You can try to see using kernel explainer. How does the time change? Do we see different explanations using kernel explainer? Can we improve the model performance using different architectures? All of that can be done. Yeah. So I guess that's all I had to present today. If there's any questions, we can move on to the Q&A.
Yes, sir. You can see the questions in Q&A session.
Just a second. Where is this? I'm sorry. Yeah. Okay. Did you say something? The Q&A. Where is it?
Yeah, there's a session called Q&A, sir, like on the label, the bottom.
Yes. Yes. Oh, okay. Okay. Got it. Okay. I'll go over a few questions. 7:30. Can you list some multitask models for computer vision? So computer vision tasks, you have tasks like object detection, segmentation, which are kind of related. So if you need to do both of them together, you can have a multitask model built for those two tasks in one shot. We still need to assess whether that's going to help or not, because not all multitasks, not all tasks are suitable for multitask learning. So it's always best to build individual models and then check if you're getting any benefit through a multitask manner as well. How does the task are defined? Where is it defined? How is it differentiated? So like in the example we saw, we had to create a, so in how it works is generally there are two types of cases. You either come up with two different requirements during a project, and you identify that they have similar features. So you can probably try building a multitask model to predict these two values. Some other novel cases would be where you only have one prediction needed, but you feel that if I define a different task within the data itself, that can help your actual prediction task. For example, in the example we covered right now, it was only a regression problem. We created a classification problem out of it, and then built a multitask model. It might not have helped in this case, but there could be cases where that can actually help. You define your own task in addition to what you actually need to predict, and that could actually give you new learnings because the model is forced to learn something else that could actually help the other task as well. So yeah, there's no straightforward answer to it. You can define tasks as you want if needed, or you can also end up with situations where you have two tasks to predict anyway. Yeah. How does knowing Shapley value and individual contribution help in tuning parameters? I'm not very sure if it helps in tuning parameters. It might, but one thing I can think of is if you find something very non-intuitive in your individual contributions, saying some feature which should not influence your outcome is influencing it, or something which is influencing your outcome significantly, which is definitely not expected, then we have to revisit our feature selection or look at any data problems, uh, or look at some overfitting problems within your model. It can also be that it's not incorrect, it's actually correct and your intuition is wrong. So it can help you in those manners. But one thing which I have to add is SHAP is as good as your model. If your model is bad, SHAP explanations will also be bad. So yeah, if the explanations are completely off, it could be that the model is also not trained properly and you have to go to a different model or revisit the training process. YOLO V5 supports three tasks: object detection, oh sorry, it's auto scrolling. Classification, segmentation. Uh, does it fall under multitask? I'm not exactly sure what YOLO V5 is covering, but if it's covering these three tasks parallelly, detection, classification, segmentation, which are actually different tasks, then it is multitask in neural network itself. Can you present Shapley values with a simple example? I'm sorry I didn't cover that with simple examples in the presentation, but I guess there are some good articles which I can give resources to which might cover these. Yeah, Kernel Shop. Kernel Shop, just to summarize, Kernel Shop is an approximation. So we know how to calculate Shapley values. If you want to get one feature's contribution, you need to create all possible combinations of other features, excluding them, including them, which are the correlations, and get the model predictions for all of those possible combinations, and then take a difference with the actual value, which would give you the marginal contribution. But doing this would be very expensive because for 10 features you'll have 1,000, for 20 features you'll have 10 power 6 correlations for each example, which you should compute. So kernel Shop just makes an approximation. It only takes a few correlations and then it tries to frame a linear regression problem. And the coefficients within this linear regression are the Shapley values of the features. and it solves that through OLS, a simple least squares errors problem. The only additional thing is each correlation is weighted in the loss function. So generally that is the idea behind it. To be honest, I don't know the exact intuition behind it as well, but the methodology which they have is that you have an approximation and you try to frame a linear regression problem with weights. What is the background dataset in SHAP? So it's something which you define. It's up to you. You define it. But the purpose of the background dataset is that, like I mentioned, you have multiple correlations. A correlation can have some features, cannot have some features. So for the features which are missing, what does it do? It samples. Let's say a background dataset is 1,000 samples. For each correlation in which, let's say, feature one is missing, it will sample different values for feature one from the background dataset, which has 1,000 values, which means it will create 1,000 samples now for your single individual sample with different values for feature one. Your feature two and three are fixed. Feature two and three are fixed. Those are the values which you have from the actual explainable dataset. But feature one is sampled from the background data. You get predictions for all these 1,000 samples now, which have different F1 values by the model, and then you take an average. That average prediction is said to be the contribution of the prediction of the model in the case which F1 is missing, but F2 and F3 are present. That's the approximation they make in kernel shop. The idea is that you average out the effect of F1, and the averaging out is done using the background dataset. Can you share the note as part of resources? I'm not sure which note you're referring to, but yeah, the links I've used and the notebook and all I can share. I have actually, it's on GitHub actually. I'll share that link itself directly. Yeah. CSV file, everything is on GitHub. The CSV file, the model architecture, the notebooks, the presentation as well. It's on GitHub. I'll share that link. How do you apply hyperparameter optimization for both the tasks? So when you define your hyperparameters, you can define the number of neurons for each layer, uh, right? So when you define that, you can specify, since I'm giving names to each of the layer for the regression task and classification task, you can specify for each layer what should be the possible candidate neurons. You define a grid, and you can do the hyperparameter optimization. Your loss, so the hyperparameter optimization requires some loss to be minimized. You can define that as a default loss, which is addition of both regression and classification loss. Or you can choose some metric of your interest. You want to weigh the regression loss by a certain value. That's up to us. We can define the loss however we want. But you can still tune the individual parameters within each task separately because you have a name for each of the layer, so you can define their parameters. How is the weight shared between the back propagation? Weight is not shared. I mean, for the shared dense layers, yes, it is shared, but for the individual tasks, it's not shared. What is shared is the loss. So the final step is you compute the loss for classification regression separately, but then you add them up. And then you look at the total loss. This total loss is backpropagated throughout both the regression head and the classification head. So let's take an example where your classification was perfect for a sample. You gave the exact correct prediction. The classification loss will be zero. Regression loss will be something because you didn't do that well. Because the overall loss is non-zero, your classification head will still get affected. Even though the prediction was correct, your weights will get adjusted because the propagation happens throughout the whole network. In that case, yes, those cases are problematic, which is why MTL is not always beneficial in cases where, sorry, in certain cases, one might influence the other negatively. So that's what we should monitor. We should look at individual task performance as well as the multitask performance. What is the need of modeling two models together? So let's say, yeah, there's a few benefits. The most obvious one is efficiency. So you need to only, let's say you have two tasks, you create two models. You will, when it comes to industry, we'll need to maintain these models. We'll have they'll have some compute costs associated, some storage costs. They should have their own input data pipeline. So by having a single model, you can avoid all that. You can just have one simple model, a lighter model, then two separate ones to get to get predictions. In certain cases, they can be better as well. The two tasks can complement each other, and because in the shared layers see both the outcomes. One task can learn some representations which help the other task. So in such cases, you get a performance benefit as well. We have the example of BERT, right? BERT has two tasks which it's trained on. If it's trained on only one of them, we're pretty sure it won't perform as well. But since it's looking at two different types of tasks and trained together, they're seeing that benefit. So yeah, in short, there's some performance benefit you can leverage, and there's also an efficiency part to it. You can make the model lighter, you can save cost. SHAP values of all features will come after trained model. Yeah, SHAP, it needs your trained model. The purpose of SHAP is to explain your model itself. So you need to have a trained model, and then you need to have the model predictions. So when you pass model to the SHAP deep explainer method, what it does internally is it computes the model prediction. It takes the model and then it takes the input sample, gets the prediction, and then tries to estimate how much each feature is contributing to that final prediction. So we need the trained model. Yeah, data alone is not enough. Difference between SHAP and feature importance, partial dependence plot, line. Okay, feature importance doesn't really tell us, it doesn't give us directionality. We don't know what the influence of a feature is on the output. We just know on the overall level, for example, a tree-based model. The tree-based model saw the most gain by splitting on this feature. We don't know if that feature is influencing an output positively, negatively. We don't have sample level explanations because feature importance is a global metric, right? Even partial dependence plots are the same. I'm not sure what ICE is, but Lime. So Lime is, if you actually look at it, Lime is kind of similar to kernel Shop, but because Lime also looks at one sample at a time and it tries to create some synthetic samples around it, fit a linear model. But one difference which I can see is kernel Shop is weighing each sample based on the coalition. How many features has it considered? How many has it not considered? Lime doesn't do that. Lime is a simple linear regression at each sample. So, and there are some other properties of SHAP which going through the documentation you'll find. They say it is locally accurate and that it has a missingness property and it has some other property. I'm not totally sure, but they say SHAP is the only one which satisfies all these three properties and Lime does not. But that you can find in the documentation of SHAP. In this specific problem, no, multitask might not be beneficial in this specific problem. I had to find some data which I could share on a public forum to unstructured data. So I just artificially created a task of classification from this, but it might not. You could all maybe it benefits also, but I'm not sure if it benefits or not in this case. Yeah. But one thing is, so one classification task you have here is predicting very high value number of shares. So the model tries to focus on getting those right. It might push your model to predict higher values better in the regression state. It's just a hypothesis, it might be wrong, but since you're forced to get some classifications right as well, your model might tend to predict a higher value better than before if you did not give that. So that might be one thing, but I'm not sure if it's happening. How explanation was sharply different from tree-based? I explained that a little earlier. Any reference material? So this time, I'll ask the host itself, like where can I share these materials? If I give it to you, you can give it to the audience, right? How does it do the right trade-off? How does it do the right trade-off between losses? So the right trade-off is, I actually didn't cover that part, but that's a good question. there is not a trade-off being done here. Let's say you have a regression problem and a classification problem, you would expect the mean squared error to be much higher than the binary cross entropy loss. So in that case, the model will prioritize the mean squared error loss only, because that's much higher than the classification loss, and the model tries to reduce overall loss. So in our problem, that was not the case, because I scaled the output values for the regression, and that brought down the mean squared error loss to a scale between 0 to 1 roughly, which was similar to the binary cross entropy loss. So it was kind of equally prioritizing both of them. But if you want, but in that case, even if scaling doesn't work for you, we can create our own custom loss. We can scale down the losses for regression by, let's say, a factor of 4 or 3 by observing how the model is training, because you can get epoch level losses. You scale your regression loss by a certain value through a custom loss function, and then you try to see how the model performs. What you're trying to do is the task which has a higher loss is going to be prioritized, higher magnitude of loss. So you need to bring them to the same scale, either through scaling your output values or either through scaling your loss function itself directly, so that that is handled. So in the code, I think I had a function where I defined custom mean squared error, which that code will be shared with you. In that, I'm just scaling it down by 3. So in that case, you will observe that the mean squared error loss is going to be reduced by 3. I'm not using that though, but in case you want to define a custom loss function, you can follow that and specify, pass that loss to the compile of the model. Yeah. I think I covered all the questions here. Thanks for the questions.
Thanks a lot, Satish. On behalf of Analytics Vidya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future.
Yes,
I hope
thank you for the
everyone,
opportunity as well. Yes. Just let me know where I should share the material covered in this topic. As yeah.
I think, like, is there any option if the link, if you can, yeah, GitHub link, you can share your GitHub links here.
I should share it here itself in the chat.
Yeah, you can share, you can do that.
Okay, I can do that. Okay.
I hope everyone has filled up the. And everyone, please fill the feedback poll before you leave. Like, I hope everyone has filled up the feedback poll. If not, I request you to please do, as your feedback is valuable and helps us to conduct more such knowledgeable sessions. If you wish to conduct a webinar or are facing difficulty in registering, connect with us at data@analyticsvidya.com. The recording of the session will be available within 2 days on our YouTube channel. The link is in the chat session. We'll be having another session from 8:30 to or 8:30 p.m. The link is in the chat session. Hurry up and register for that. See you in the upcoming data sessions as well. Till then, bye bye and keep learning. I hope you like pasted the GitHub link, sir.
Yes, I pasted it. It's in the chat. Yeah.
Yes, and everyone, please fill up the feedback too.
Great. I can
Yes, sir.
drop
You
off it.
can. Yes, sir. Thank you. Thanks for
Cool.
having us.
Thank you very much.